it's 0.1239, unknown alpha of CP prime, cosine of beta, but beta was 23.8 degrees, and that must be equal to the I stuff on the other side, which is going to be 15 times 15 is 225. 225 is 22.5 times a tenth there, 22.5. And that should be a minus sine 30 on that, shouldn't it? So negative, and then we have sine of 30 degrees, which is 1/2. And then the I term here is a minus term as well. Acceleration of p prime relative to p times sine of our 23.8 degrees. So that's our I stuff.
Are we forgetting the other component of that equation on the left side?
Did I miss one?
Up one.
Oh, up one, thank you. This guy right here, thank you for catching that.
And you just add in a sign to that side.
Yeah, so actually what I'll do is I think I'll leave it on the left just so it's clear. So it's, what we have in here is a plus 0.1239 with our 18.22 squared, and I guess that's actually negative, isn't it?
Yeah.
Sorry for these errors. And our sine of our 23.8 degrees there. So that stuff is all equal to the things on the right there. Both unknowns are in that equation, and that's usually the case. When we write our J stuff, we're also going to see both unknowns. So we're going to end up with a system of two equations with two unknowns. So let's carefully do that. So we have a positive 1239, 18.22 squared, cosine of beta, cosine of the 23.8 degrees, and we add the other J term, which is positive 0.1239 alpha CP prime, sine of beta 23.8 degrees, and that sum has to be equal to the J terms on the right. So we pick up a minus 22.5 again, cosine of 30 degrees is square root of 3 over 2, and then plus the J term on the tail end, acceleration of p prime relative to p's value, cosine of beta 23.8 degrees. It's usually a good idea to pause when you write an equation like this, to pause and look back at your vector equation to make sure you didn't mess a sign up somewhere. Okay. How about you folks, a bunch of you on right over here from Daniel over, 5 of you or so. Why don't you folks compute this value, make sure we get the same result. And then up here, how about the rest of you folks punch out this value right here. And I'll grab my calculator and we'll go ahead and see if we can clean this up. And keep in mind that there was some conjecture made earlier by someone that indicated that, oh, this slotted arm has 0 angular acceleration. So we're going to sort of see what happens when we get done doing the two equations. This is 2 linear equations and unknowns. It's just got some numbers tossed into it, just like beginning algebra, with a little more complexity, I guess. Okay. Oftentimes what I'll do on more complicated problems is I'll actually set up the structure of these so that I can pop it in as matrix system, solve it using matrix methods. Okay. Put my glasses on. This value, okay, so let's see. If I redo my I stuff again, I have a 0.1134 alpha CP prime, and that's equal to, on the others, I'll hold it. What was this value?
Negative 16.59.
People agree?
Yes.
Okay, negative 16 point what?
5982.
982, okay. So we have that left side stuff, and then over on the right side, it looks like a negative 11.25. And sine of 23.8 degrees is 0.4, so it's a negative 0.4035 acceleration of p prime relative to p. Our J equation, what value did you folks get on this circled expression?
37.63. Yep.
Thank you. 37.63.
Yes.
Okay. Is it near the middle of the next decimal?
Yeah, it's closer to the 3.
633.
633?
Yeah.
Okay, I'll just leave it at that. And then we're adding to it is 0.1239 sine of 23. 0.05. This last term looks like 0.05 positive. And then over on the right, we end up with a similar term. Well, actually, no. It's a negative 11.25 times square root of 3. 19.4856
Second.
minus 19.4856 right there. And then the cosine off of that 23.8 positive 0.9150 acceleration of p prime relative to p. Okay. I haven't done it with you folks this term, but I think I'm going to go ahead and set this up as a matrix. Do you folks use matrix methods with 83, 84 calculators or 89s?
Yep.
Everybody? Anybody not? Okay.
So I've done the matrix method.
Okay, so anyway, this one would set itself up, and just for the interest of the videotape, I think what I'll do is go ahead and write it up here in that format. Is we could write this, if we put our alpha terms first, then we could set this up in this fashion. 0.1134, and below it 0.05, and then we could imagine moving the acceleration terms over to the left side, and that would become a positive 0.4035, and the other one would be a negative 0.9150, and that would be times alpha of CP prime, and the unknown acceleration P prime relative to P, and that should equal then these constant terms, which I need to combine this number and this one on the right side. So I have a 16.5982 positive, taking away the 11.25 for a 5. You guys can check this, do your own work on this and see if we agree with the results. And then we have our minus 19.4856. And a minus 37.633 for a negative 57.1186. So here's a matrix solution then. And so what we can do is take the inverse of this coefficient matrix and multiply it times this column vector over here, and that'll give us these two answers. Okay. Did I set that up right, or did I mess up?
Vertical column be all alpha C P prime on the left. That should be the AC alpha C P prime, right?
Right here?
Oh, that's weird.
That and that.
I've got the terms. I have 0.1134 and 0.4035 associated with alpha C. Oh wait, no, never mind. Never mind.
Am I okay here?
No,
Yeah.
I'm reading mine backwards. It's
Yeah,
weird.
you're fine.
Okay.
Yeah, that looks good.
So what I want to do with the calculator is we'll have them put the camera on this because I want to make sure students that might use the DVD would understand how to handle this. So what we do is we go to the matrix feature of the calculator, back out a little bit. Okay. So I'll just sit down here and do this. Good. There we go. And we'll see if this shows up on this screen or not. Okay. So what we do is we go to the matrix feature of the calculator, and I need to establish matrices A, B, and C. So matrix A, I'm going to edit. So I go to edit, matrix A. It's a 2 by 2 matrix, and I'm going to input those coefficient values, 0.1134, 0.4035, second row 0.05, and last term negative 0.915. Okay, so that matrix is in the calculator. If I want to see it, I can just go to matrix name A and take a look at it. There it is. Matrix B is going to be the matrix of constants on the right side. So I go to matrix, edit again, number 2, and I'm going to set that up as a 2 rows, 1 column matrix, and it's going to have the numbers 5.3482 and the negative 57. Is that showing up on the screen reasonably well on the TV? Okay. 57.1186. So we've got that. I'm going to go ahead and zoom in a little more on the screen now. Okay, so that's in there. And then I quit. And so now, in matrix B, I usually double check these, make sure I punched them in right. Those numbers look correct. So now what we're going to do is we're going to take the inverse of matrix A and multiply it by matrix B. So matrix A, I get it, matrix A's name, and the calculator, this calculator uses the reciprocal key. When you're operating on a matrix, it treats it, doesn't mean reciprocal, it means the inverse of the matrix. And we're then going to multiply that by matrix B. And these should be our answers for both the alpha and the acceleration of P prime relative to P. So what we get out coming out the door here is that alpha of CP prime is fairly large, negative 146.5 approximately, radians per second squared, which means negative means which way?
Clockwise.
clockwise. So this is clockwise. And this is making an assumption that all the math we did earlier was okay.
Not
And
necessarily.
then we picked up that the acceleration of p prime relative to p is this other value, 54.4 meters per second squared.
And do you need to multiply that out into the normal and the tangential? Because you've got that vector that has the two different directions. Would you want to multiply that value by the two vectors to actually get you normal and your tangential values?
Well, these are these two elements. These two magnitudes. These are the two magnitudes that were in these scalar equations that we came up with. So let's come back to your question here now. What are you commenting here? I'll get to you in a second.
This is
Daniel.
where the a of p prime relative to p is.
Yeah.
Now down in your equation, would you multiply your value there that you got times your, not the projection, but that in order to get the normal and the tangential values?
No.
No.
Don't worry about it. We don't worry about it. Okay. So the things we're worried about, like this, remember what this is? This is the relative motion or the relative acceleration between those 2 points that are coincident with each other.
Oh,
And it's always got to be along that line of the slot.
okay.
It has to be along the line of the slot. So we're not too concerned about the sine and cosine components coming off of those.
Okay.
And keep in mind also what these are. This is an I term.
Right.
There's an I term here and a J term.
Okay. So that-
Okay? So they're just two orthogonal components of that thing that, again, has to point back up
Along
this
the-
way.
okay.
Yeah. To clarify the earlier place where I made a mistake in the way I was setting this up, is up here, this orange-colored stuff is indeed correct, those two components, and those, though, are what exist over on this left side of this equation here, on this acceleration equation. Okay. Now, how can you tell if that stuff, those values we came up with, are correct? Now, before I answer that, let's see what Daniel's question was.
We didn't define theta in a standard direction.
Well, we defined it relative to a non-moving, a vertical reference axis. We measured it clockwise off of a vertical. So that's perfectly fine.
Okay, but
And we wrote, I believe correctly, all of our x and y components as needed, related to that defined angle theta.
okay, so even
Yeah.
though we defined theta going in a non-standard direction, and furthermore we even mixed it in with a beta which was defined in the standard direction, we can still assume that the standard clockwise, counterclockwise, positive and negative association holds for acceleration of Cp prime.
Acceleration of c p prime. Yes. Okay.
Okay.
Now, how do you check to see if these numbers we came up with fit together properly and are indeed correct? Without having somebody, an independent researcher, go in and doing the same calculation over again.
Vector diagram.
Vector polygon. So let's see if we can draw a vector polygon of this acceleration stuff. Okay, and I hope we have the numbers laid out here reasonably well. I think what I'll do is come back over here and take a little bit of space to make sure we have the different components. So what is this value? Right here, somebody punch that for me. At 0.1239, 18.22 squared.
41.13?
No, it's got to be big. Oh, well, that's like 400, a tenth of 400 is 41 point?
Yeah, 41.13.
Okay. Okay, 41.13. And the units on that are what?
That would be,
Folks, think about that.
Units
Borrowing
measured
meters per
acceleration,
second,
so
meters squared.
meters per second squared, right?
Acceleration.
Okay. And what acceleration is that?
That's the acceleration as a result.
That's the normal acceleration of p prime relative to c. P prime relative to c, normal. In other words, it's a pseudo-normal. It's pointing back towards c. Everybody okay with that? It's this guy that I drew in orange on the other board. Okay. What is this now with our calculated value? With our alpha over there, minus 146.5 times a tenth, roughly. Like 14, 15, 16. What's that value? Somebody punch that. 0.1239 times the minus 146.5.
That would be negative 18.15.
Okay, that sounds right. 18.15. Again, meters per second squared. Okay?
18.5, 18.2. Still not that bad.
18.2 is fine. Okay. Now, so we got those two on the left side. Acceleration p relative to o. What's this? Distance OP is a tenth, and our omega OP was
That was the 18. No, it's not. It's a 15, right?
it was 15, wasn't it? So here we are, 222.5. Okay, so that's the acceleration of p relative to o, and that was 22.5. Is that right? See how much time? I got about 4 minutes left is all. And then we got that. And then what was this guy? Acceleration of p prime relative, oh, there it is, 54.4. P prime relative to p, 54.4 meters per second squared. Okay, what I want to do is take these four values and see if we get a polygon that ends up closing properly. Okay. We'll come over to the last board here. And see what we have. So what we do is we look at the governing equation. P prime relative to C. P prime relative to C has a normal that points from P prime back towards C. And so we have to go up, and this is 23 degrees, 23.8 degrees off of the vertical. So we have to draw ourselves a vector that's of length 41.13 back up that way. Okay? Then orthogonal to it is a vector that points down and to the left with an 18.15. 18.15 is a little less than half of this length. That look about right? Okay, keep in mind what these are. This diagonal right here, folks, is the acceleration of p prime relative to c. This diagonal here. Okay? That is the left side of our equation. Then the right side of our equation, we come back to the pole, and we now want to go acceleration of p relative to o. P relative to o has to be at 30 degrees off of vertical. .30 off of a vertical and pointing back down this way towards O. P, I'm doing this guy right here, and that has to be a 22.8, 22.5 at 30 degrees. 22.5 would be about that long. Okay, and then this guy, acceleration of p prime relative to p, the last term here, has to be pointing with magnitude 54.4 back up here at angle beta 23.8 degrees, and that should be a 54.4. And keep in mind what that is. That's the acceleration of p prime relative to p. Okay. I think we don't have time to finish this off, but how would you check to see if this indeed is correct, if this all closes? In other words, the left side stuff, this thing, is equal to the sum of this and this. How would you check it? You have the geometry. Well, you have the geometry on this polygon here. Here's beta, there's theta off of vertical, there's 30. There's the, you know this angle here, you know that's 90 right there. So you could check these numbers and see if this polygon actually closes. Okay, so these things are long-winded, obviously, and it's a little difficult trying to present them in an understandable fashion, but you just have to write the long details out, all of it, and then just take and then just step your way through it carefully. Okay, so I hope that helps you a little bit. Okay.